I was thinking SpongeBob. You know,
I love SpongeBob.
actually, I'm not gonna say that because I don't want to embarrass myself.
Okay. Just check, make sure energy's still. Okay. All right.
Always in here.
So let's start with question number 4. Some of you have been debating this. Okay. Look, to make the units work out, you have to put force on the y-axis and you have to put elongation on the x-axis. Otherwise, you don't get joules when you look at 1/2 kx squared. Okay. Yes, it's kind of somewhat counterintuitive because you're used to thinking, oh, force is the independent variable. And it is, but to make the units work out on this graph, you have to put force on the y-axis. So your slope on 4A should be around 20 meters or 20 newtons per meter. Okay? Because if that's wrong, everything else is going to be wrong. So you always assume that the spring obeys what's known as Hooke's law, which basically Hooke's law is nothing more than saying, hey, a spring stretches in a linear fashion. That's all it really says. So you can always assume that 0, 0 is 1 point because you're graphing elongation. Okay, you're not graphing length. Okay, that's why that graph starts at 0, 0. So you can find the slope of the line, boom, you're off to the races. Now, when you get to B and want to calculate the work that's done, okay, there's 2 ways you can do this. You can either go to your graph and you can find the area underneath that line, which is going to represent the work, okay, or you can do the work that you're going to do is 1/2 kx squared, where x is your elongation, okay. What you cannot do is treat this as a rectangle and just take that force times the elongation, okay? Because it isn't the same amount of force acting over that entire length. Springs, the farther you stretch it, the more force it takes. So what you cannot do is just take force times elongation, because it's not a rectangle, it's a triangle. So you either find us using the K value, or you find the area underneath that graph. I care not which one you do, but you have to do one of those 2. If your answer to 6A is wrong, everything's going to be a train wreck. So your answer to 6A should be right at 2 joules, because that's how much energy that you have in the system. Okay. Your answer to 7A on that velocity would make it GPA. Okay, not completely stellar, not completely horrible, just okay. Now, let's talk about number 8 with the bungee cord. Okay, so here's your setup. So you're standing on top of this bridge, okay, and you're going to fall. So initially, as you fall, the only force acting on you is gravity, because until you hit the end of that bungee cord, gravity is the only force making you fall down. So your answer to 15A, and this is an ish, is going to be something around your current age. Okay? It's a huge ish, but it's going to be something around that. Okay? Now, after that bungee cord hits, okay, and this thing begins to stretch. As it stretches, what happens to the upward force acting on you the farther the bungee cord stretches? It increases because F equals Kx, okay? So when you get down to the bottom like this, okay, the bungee cord just broke. When you get down to the bottom, okay, then here's the easiest way to work this problem, is that you have to find the K value. So imagine that you're down here and that bungee cord is stretched as far as it's going to go, and you're SpongeBob. Okay, let's go with the SpongeBob theme. Okay, so there's SpongeBob at the end of the bungee cord. Ah, kind of clever. And so he ends up 31 meters below the bridge deck. So if you reverse the process and go, okay, well, how much UG is there in the system? Well, your UG in the system is going to be mgh, which is going to be that 31 meters, okay? Because that's that gravitational potential energy that you're going to store. You really can't talk about kinetic energy because at the bottom of this, he's at rest. Okay, so there's no kinetic energy at the bottom. But what you have done is that you stored energy in that spring. So what you do is set the UG equal to the US. Okay, so the energy stored in the spring is equal to the change in the gravitational potential energy to, in effect, lift him back up. So this is going to be 1/2 kx squared. This is going to be mgh. And nothing is going to cancel out. But the trick here is the 31 meters needs to be the value for your height. And that x is how far the bungee cord stretches. Okay? So if all goes well, that K value should be around 100 newtons per meter. Okay? It's an ish, but it's going to be something close to that. So on D, when I'm asking you to write an expression for that net force, okay? Obviously, you want him to accelerate, okay? Because if you don't accelerate, bad things are going to happen. So if you think about it, it's like here they are. You're at the bottom of this oscillation. You're way down here like this. So you have two forces acting on you. You have the bungee cord acting up, and you have gravity pulling down. It's like a tug of war. If you're going to stop, which one has to be bigger? Yeah, the force from the bungee cord. That has to be bigger than the force due to, oh, there he goes. And that's what happens when you don't have a bungee cord. Arrows down. So when you get down here like this, okay, so you have a force from the bungee cord acting up, you have gravity acting down, and the difference between those two is your net force. So, and the force from the bungee cord is just going to be kx. At that point, you know the spring constant. You know how far the cord has been stretched. So you can find the upward force from the bungee cord. You know his mass, so you can find the gravitational force acting down. The difference between those two is your net force. So your answer to 8E should be something close to the legal drinking age. Not what it is when you folks are out of town. Morella.
Can we go over 9? Because I did it the old way, but I think that we weren't supposed to do that.
No. So in number 9, there's two ways you can work number 9. There's an old school way, and then there's the new school way. So on number 9, you're going to launch this ball at an angle like this, right? And it's at 45 meters per second, or 45 degrees, and 185 meters per second, which is pretty fast, and you are 265 meters above the ground. Okay? There you go. So here's the deal. There's two ways you can do this. The old school way is that you're going to come through and you're going to find Vx and you're going to find Vy. So this thing is going to go out here like this and it's going to land. So since it's talking about the speed, you have to have the Vx component when you land and you have to have the Vy component when you land. And then you have to take the hypotenuse of that. Okay? Leslie, you just shake your head. You have no part of this, are you? No. Okay. Now, you have your Vy, so you got to go through and use that equation and find your maximum height. Add that to 265, so then you know how high above the cliff you are. And then it's going to fall all the way down, and then you're going to find a new Vy, which has to be bigger than the initial Vy because it's falling 265 meters down off the cliff. Then you're going to know both of those components, and then you find your hypotenuse. It's old school, it's smash mouth physics, but it works. Okay? It does not get the Leslie seal of approval. Major head shake, having no part of it. Now the other way that you can go is like, Burke has been teaching us about energy. Okay? That gets the yes head nod. So from an energy perspective, what two types of energy does it have at the top of the cliff? Again, KT, right? So we'll call that KT naught, right? That's that initial kinetic energy. Now, do you have to have the angle to calculate this initial kinetic energy? Why not? It's just 1/2 mv squared. The angle that it's launched at does not matter. It could be at 45, 60, 30, whatever. Horizontal, down. Doesn't matter. Doesn't matter. Same amount of kinetic energy. And then that's going to be mgh. We'll call that V naught. Now, when it lands, what's the only type of energy it's going to have? Kinetic, which is going to be 1/2 m, that's the final kinetic energy, 1/2 mv squared. So if you're clever, which you all are, why did I not give you the mass of the ball? Doesn't matter. Cancel that out. And if you're also clever and you're like me and you hate fractions, what are you going to do? Multiply by 2. Then you get 2gh plus V naught squared equals V squared. Otherwise known as that equation. So that's the easier way to do it.
Oh,
I shouldn't have answered here.
What do you want it to be around?
199.
Is it?
Is it 199?
What if I just use?
I didn't
I did
rate
that
my
just using that
calculator
equation
was
one
not
time.
but it's still
It's like it's
199.
gonna be 188
Wait.
back when it hits.
Wait.
Like when it comes back down to where it was up, thrown up, and you use that equation, I got 199.
Yeah, you can.
Yeah. It's only yeah.
What's 4B around?
4b, what do you want it to be around? It's around 0.1.
Okay.
Wait,
Where's 4B? Give me 4B. Where's my
Topher.
4B?
What did you say?
Hold on, so we had it right, basically.
Which one?
8B.
8b,
What numbers are these?
that swing constant, it's around 100, a little bit
I
above.
forgot to put it in one.
Won't you be back?
Okay, so I had it
Oh,
right the first time, but it's still 198.
9.
I think it's like 198.
Anything else?
I just
No, sir.
Going once?
Wait, did you say 4B was around 0.1?
Yeah.
is 4C 0.25?
You want it to be?
I don't know.
Yes.
Yeah. Okay.
When's the test for this?
I don't know, I've got to look and see exactly how many more days we have. I've got to formulate
Where'd
the
you
big
get,
picture.
one?
Is it just energy on this, or do we have another thing in it?
I don't know, that's what I got to figure out. Because we still have to do rotation.
Okay, so I had it right. Okay, we're good. I don't know
So-
why.
Today is what, Thursday, we got a lab today. Earliest would be probably back the middle of next week. So it's just an energy test. So we'll see. Okay,
Okay.
anything else?
I had it right. I was
Going
right.
once, going
I did
twice.
it right last
So,
So I did it right last night, I just didn't square it. Yeah.
so here's the deal. So this lab is kind of cool because it's going to go old school back to the very first lab that you did, but yet new school in terms of energy. Okay? So the setup is going to be, you're going to have a setup like this. Make sure that you clamp this down so that it doesn't tip over and everybody goes BAM! Okay? So on the bottom of the lab there's a diagram and it actually shows it having like a hook clamp. Don't do that. Because our hook clamps don't line up with the center of these rings. So you want to have a ring at the top and just take a round metal rod and hook the string through that like so, and that's going to oscillate like this, okay? So the first thing that you want to do is take one ring and raise that up so that the bottom of that ring is level with the bottom of the spring. Sounds like a Dr. Seuss thing. Make sure the ring is level with the spring. So you got that action going, okay? So the first thing that you want to do is find the spring constant. And this is what we talked about. You're going to have to draw a graph, and you're going to put force on the y-axis, and you're going to put elongation on the x-axis. That's the only way the units are going to work out in terms of ending up with energy. So on the lab, up here, I tell you specifically which masses that I want you to use, okay? So 0.4, 0.5, 0.7, okay? So you're going to take, for example, that 0.5 kilogram mass, and there goes Hank rolling across the floor, and you're going to have a certain elongation. So this is elongation. This is not the length of the spring, right? So you're going to measure from here down to here, okay? From your measure bottom of this one down here. You're going to get this, you're going to stretch it further and further and further and further and further. Further you stretch it, the more force that you're going to need. Hooke's law. So you're going to generate a graph. You're going to have some points. And listen to me. You're going to draw a line of best fit. Okay? It should be pretty linear because they obey Hooke's law. It should be pretty linear. So you're going to draw a line of best fit. Okay? And then you're going to calculate that spring constant. Typically, with these springs, that spring constant is usually around 60 to 80, okay? Kind of a ballpark about where that's going to be, okay? Usually around 60 to 80. So you're going to get that number. So that's the first thing you need to do is hang those weights, get them stretched out, then you're going to draw a line, you can have a line of best fit. Now, in the instructions, I explicitly tell you what I want done. You're going to pick a couple of points on that line of best fit. And you're going to write down what those X and Y coordinates are, because everybody's going to be a little bit different. So again, focus on the process. I should be able to look and see exactly which points you picked, and at some point, either on the lab or on that graph, show me how you calculated that slope, because everybody's going to be a little bit different. I can only grade your process. Pick the points, boom, and you can use 0, 0. If you want to use 0, 0 as a point, hey, that's valid. Okay, 0, 0 is just as valid a point as anything else. But you can draw that line of best fit. Now, the other thing that you're going to do, and this will make sense later on, you're going to need this later on in the lab. You're going to come out here to where your maximum elongation exists. Okay, so with that one of 1.5 kilograms, you're going to find that maximum elongation. This is why I've got that little asterisk in that cell. Okay, that's why that's there. See, Mr. Elliott? So that's why that's there. So you're going to go to this. You are going to draw a line straight up from that point. Where it crosses your line of best fit. Okay? This is going to be huge later on. And then you're going to circle that point, and you're going to write down what those X and Y coordinates are. Now, if that happens to be that same coordinate that corresponds with 1.5 kilograms, cool, okay? Usually it doesn't, but sometimes it does. But no matter what, you're going to figure out where it crosses that line of best fit. You're going to come over here and you're going to figure out how much force corresponds with that maximum elongation, okay? So you're going to go to there, draw a line straight up, boom, there you go, okay? Because what you're going to do eventually is you're going to find the area underneath that graph. And that way I know which point that you're picking in terms of finding that. So you're going to find, I tell you this in the instructions, but you all are horrible at reading the instructions, so this is why I'm going over this. So go to that maximum elongation. Straight up, find it where it crosses your line of best fit, go across, boom, there you go. Got it? Good. Okay, that's the easy part of the lab. Now the second part of the lab, you're going to make it oscillate in these rings. So with this one, you need, if you look over here on page 2, you're going to do this with 1.2 kilograms, and you're going to do this with 1.5 kilograms. So here I've got 1.2 kilograms. Hook this up, like so. Okay. Now this is why you want to use these rings and this rod, so then you can adjust them so that it's right in the middle of these rings. So lift this up, kind of like here-ish, and then have this something here like this. Okay. So what you want to do is you're going to make this thing oscillate in these rings. Okay. So the first one you want to do is a small amplitude. Amplitude is referring to how far it moves out of its equilibrium position. Okay? So you're in a fairly small amplitude. So what you want to do is get it oscillating and then adjust the rings after it begins to oscillate. Okay? So you want the top ring where this is level with the bottom of the spring when it's at the top of the oscillation. And then you want this one level at the bottom of the oscillation. Okay? So you're going to get it going like this. Okay? So, you know, something like that. Okay? Do that a little bit. There you go. Okay? So get it oscillating. There you go. Now, let's talk about what's happening. There's 3 types of energy involved in this oscillation. What are the 3 types of energy? Jack, ring, what's one of them?
Potential spring.
Us. Let's talk about us. Okay? Is us going to change as it oscillates? Yes. Why, Jack?
What if I can?
I didn't mean to catch you mid-mouth. I'll defer to your esteemed colleague to your left. Mags, why is that? Why is us going to change as it oscillates? Because what? Mags, how do you calculate us? 1/2
KX squared.
kx squared. What does x represent?
The elongation's changing.
So since the elongation is changing, my us is changing. Okay, now here's the $1 million question. When do you think us is at its maximum? Do you think us is biggest at the top of the oscillation or the bottom of the oscillation? Bottom. Why? So when it stretches the farthest, right? Okay. So it's going to have its maximum us at the bottom, and it's going to have its minimum us at the top. Now, in this situation, do you think us goes to 0? Nikki B, you shake your head no. Why?
Because it's not that. It's like.
Yeah, it's not at its equilibrium point. Even at the top of the oscillation, we're still going to have some us. Because for the us to go to 0, that would have to go all the way back up here to the top. So even though it's like a relative minimum and maximum, it doesn't go to 0. Okay? So we're going to have some us, but that us is going to change because we're changing the elongation. Okay? What's another type of energy? Gracie. There's 2 more.
Kinetic.
Kinetic. Why does it have kinetic energy?
It's moving.
Because it's moving. Right? Kinetic energy equals 1/2 mv squared. Now, think through this. Does the kinetic energy ever go to 0?
Yeah.
Cooper, you kind of gave this very distinguished scholarly head nod. Why?
It changes direction.
Okay, changes direction. So when does the velocity go to 0?
When it changes direction.
Changes direction at the top and
And the
at the
bottom.
bottom. So in any oscillation, you have 2 situations where the kinetic energy goes to 0 because you're going to be at a 0 at the top and you're going to be at 0 at the bottom. So if you're at 0 velocity at the top and you're at 0 velocity at the bottom, when do you think you have your maximum kinetic energy?
In the middle.
In the middle. Okay? So it falls, it speeds up until it hits the middle, and then it begins to slow down. And then it speeds up, hits the middle, and then it begins to slow down. Okay? So kinetic energy is always changing, but kinetic energy is going to go to 0. Okay? It's cool. So oddly enough, our kinetic energy is going to change as well. So it's a 3rd type of energy. What'd you say? Ugh. Is Ugh going to change?
Yes.
Oh wait, no it doesn't.
Yes, it does.
Wait, no it doesn't.
The
No,
height
yes, it does. Yes, it
movement
does.
moves. The height changes.
I was right the first time. Ignore the second time.
Okay. All right. So Is the height changing?
Yes.
Yes, so guess what? UG is changing. So when do you think UG is going to be at its maximum?
Top
At the top or at the bottom?
top.
Top. UG is going to be at a minimum at the bottom. So what you're seeing is that this is like a 3-container system. Okay? You have an UG container, you have an US container, and you have a kinetic energy container. Okay? So all you're doing is you're continuously siphoning this energy between the three. Now, if I let this go long enough,
Is it gonna stop?
what's going to happen?
Stop.
It's going to stop.
Oh.
What'd she say?
We were gonna ask
We're
if it
having
would
a
ever stop. Me and Gracie though.
No, it's just.
But it kind of just
Gracie and
doesn't-
I. Thank you.
Grammar Nazi?
Yeah.
No, Gracie and I is only when it's a subject.
But you
Okay.
always put me and I after. That was a subject.
No, it wasn't.
Okay.
Wait, I think. I don't know.
Okay. So, here's the deal. So, it is eventually going to stop. So, what's the great dissipator of energy? Thermal, friction. Okay? So, what's happening is that as that spring is vibrating, okay, then that fundamentally what you're doing is you're making the particles that make up that spring vibrate. You stretch them, and they go, oh, I don't like this, I want to go back, okay? And then you stretch it and it goes back, right? And at a molecular level, they're not happy, okay? And what's happening is that they're heating up. Now, it isn't like, wow, let's do this and the room is cold and I'll make a spring oscillate and I'll warm up the
I
room.
wonder why it's
Okay.
so hot in here.
Wait, so does all kinetic energy have what's it called? A release of thermal?
Yes.
Oh, so
long
then
as it's colliding with
technically,
something.
well then wouldn't that mean that things can't go on forever for
That's why you
in
can't
a
have
vacuum?
perpetual motion.
Oh,
Yes.
okay.
Now, so the particles that make up the spring, right, are vibrating. So they're going to warm up. Not a lot. It isn't like I grab this and I burn my hand, okay? But I'm going to lose some energy that way. It's moving through the atmosphere that we have, right? Nitrogen and oxygen molecules, they're colliding with that. That's taking away a little bit of energy. So over a period of time, it's all going to stop. So thermal energy in the form of friction, internal energy of the atoms as they're stretched and moved back, that's your great dissipator. Now, what if we did this and I put like a flat piece of cardboard on the bottom and made it oscillate with a piece of cardboard on the bottom? What do you think would happen in terms of the length of time it would take to go to zero?
Decrease.
Why?
Because there's more friction with the air.
Yeah, there's more friction, right? It would stop sooner because of the fact that you would be dissipating more of that energy with friction. Okay? So, now, turn to page 1. So, on page 1 down here at the bottom, you have 3 specific measurements that you have to have, okay? And they define how the calculations are going to play out later on. So the first distance from the top ring down to the first ring, which is at the top of the oscillation, this is what we're going to call x1. So what that represents is how much potential energy there is in the spring when it's at the top of that oscillation, okay? This isn't when it's stretched. This is x1 after you make it oscillate. So this is x1, which is going to represent the first energy stored in the spring. x2 goes from here all the way down to here. Okay? So that represents the second amount of us. So you're going to have 2 us's involved. us1, us2. And the difference between those two is what we're after, okay? We're going to try and figure out how much energy changes in terms of us as it oscillates from here down to here, okay? That's what you got. Now, H is going to be the difference between the bottom ring and the top ring, because that's going to be the change in your gravitational potential energy. So over here on page 2, once you get that thing to oscillate, the first one is going to be the smallest amplitude. So x1 I'm going to measure from here to here. x2 is going to be from here all the way down to here. And then h is going to be this difference between the two of them. So you can either subtract x1 from x2, or if you just want to measure h directly, I don't care. Okay? But so when in doubt, reference back to the front of that page. Here's x1, here's x2, here's your height. So you're going to do 3 different oscillations. You're going to have 1.2 kilograms with a fairly small oscillation. Then you're going to have 1.2 kilograms with a bigger oscillation, okay? And you got to keep everything centered. That's the whole key to this, okay? Then you're going to swap it out, and then you're going to put 1.5 kilograms on it. And this is why, again, you want to make sure that you've got this thing anchored down, because you're going to have a lot of weight out there on the end. So then you can, oh, catch that. Then you're going to have this action going. This is tough to do with just one person. No, I got it. Years of practice. Okay. So you're going to have 1.5 kilograms, and you can have that action on. And the more weight there is, the period actually becomes slower. It oscillates slower the more weight that you put on the end of it. Okay, so those are going to be your 3 oscillations. So what I want down here for trial 1, okay, I only want to see the calculations for trial. This is on page 2, okay, down here towards the bottom. When I say show calculations, I don't mean write down the formulas, okay? When I say show the calculations, I want to see the numbers, okay? So you're going to show me, hey, this is how I calculated U1. 1/2 times your spring constant times x1 squared. Same thing with 2. You're going to subtract them to find delta us. UG is going to be mgh, okay? So here's the whole idea. This operates because you're continuously changing the same amount of energy is always present. You're just changing its form. So what should happen when you compare change in us to change in UG, you should see that that difference is really, really small. In an ideal world, they would be the exact same values, because all you're doing is you're just changing that from one form to the other. You always stop, because you're always losing friction. Now, one of the questions is going to be, what would happen if you tried to do this lab in a zero gravity situation, if you were in orbit, okay, or in zero gravity? So visualize this. I would pull this down, okay, and then I would let go of it. But there would be no gravity. So imagine what would happen if visualize this. This is a straight shot, okay? I would pull this down, and I would let go of it. Obviously, it's going to begin to accelerate upward. Would it stop? Okay, or what would happen? So that's going to be one of the questions. So visualize this. I pull this down. As soon as I let go of it, I have no gravity. Okay, what would happen to the weight on that system? So you don't need to have the graph drawn to get all of the data, but you have to have the line of best fit to do the calculations, okay? So, I'm done. You're on your own. There's rings, there's stands. When you all get done, take everything back apart. Stop me on the camera.